All right, welcome. So happy Friday, I guess. So today we're just going to talk about logistic regression, and I cheated a little bit because it's a pre-recorded video, so I did pull in all the notes from the summary notes, but they are the same, just rest assured. But I pulled them in so I don't have to go back and forth. So far we've talked about what are some of the methods that we can use to make sure that we select a good model, right? It has to perform well on a training set before it can graduate to a validation set. And then we have to check it against the test set, which is the ultimate test, right? Where we see how well a model performs. Now, and then we said, okay, well, what are some of the performance measures that we can apply? And we focused on classification methods, right? And so we focused on categorical outcomes, because for continuous outcomes, then it's just based off of the residuals or the errors. And then we can just kind of, there's tons of stuff we can do, right? But it's all focused on the errors. And same with classification, but it's a little bit different, right? Because we talked about, okay, so if I predict that something is going to be in class 1, then I could be correct about that. That's good. Or I could be wrong about that, right? Same thing, I could predict that something is going to be in class 0 when it's actually in class 1. That would be an incorrect prediction, but it would be in a different way, right? And so we talked about, okay, what are some of the measures that we could look at to compare different classifications? And now today is the first time that we're going to see an actual classification method. And so logistic regression is kind of the most common one that we use, as assuming that we have some binary outcome. Okay, and so we have this, we're classifying some binary, which means it's a 0-1 outcome, right? So we have a categorical outcome. So we want to classify, a categorical outcome with only 2 levels, right? The 2 categories is either 0, 1, right? Basically a dummy variable, right? But those are placeholders for something happening or something not happening, right? So for a classify a categorical outcome with 2 levels, I'll say. With 2 levels, 0 or 1. Okay. So now we're trying to predict, are they in class 0 or are they in class 1? Now we can look at, I think the example in the textbook is using Oscar nominations. So you can have a number of Oscar nominations, and then we've determined if they won Best Picture or if they did not win Best Picture, right? So there are really only 2 outcomes here. So trying to model it with a linear equation here kind of makes no sense, right? Because here, this group didn't win. They had some number of Oscar nominations, so that's great. But only this group won, right? With a probability of, well, I guess not really a probability, an outcome of 1, right? So these guys won. Whee! So we could look at this, and our software never hesitates, right? Whatever we ask it to do, it'll do. So we could fit a straight line here, and we could We could find an R squared. It's not very high, right? So there's lots of things that we could do. It just doesn't make sense in this case, right? And so part of the problem is that this line goes and extends beyond 0. And technically this line extends to positive and negative infinity, right? Going off in opposite directions. So, but we know that if the outcomes are just 0, 1, we are restricted to that space. Okay, and so that's part of the problem that we're dealing with here. If we decided to still go ahead and use this line as our prediction, that's weird, but okay. Let's assume that we did. Then our residuals, so our residual plot would look like this, right? Remember, for our residual plot, we're looking for random scatter around 0. I'm seeing patterns around 0, so that's a really bad sign, right? So this straight line, the plain linear model does not fit the data well, is what this is telling us. So from here, I'll say the plain, meaning just the regular linear regression line, the plain linear regression line, which is our y hat is b0 plus b1x, does not fit the data well. All right, that's what we're seeing here, because we are looking for random scatter around 0. Okay, so here, got it summarized. If we try to use this function, and we can even extend to more than one x, so more than one predictor, but what happens is we need some way to capture the fact that this line can't go below 0 and it can't go above 1, right? So we're restricted to the range of 0 and 1 inclusive, because both of those can happen, right? And so what we do is we make this S-shaped curve. Okay, so what's nice about the S-shaped curve is that it'll have an asymptote at 0 and at 1. I think it might even get there, but I'm not in, I'll have to think about that. But anyways, so that's how we get it to kind of stop between 0 and 1. Okay, and so now what we're going to be able to do is, so notice that these values here, if we're running between 0 and 1, then those are probabilities, right? And so here now, because I'm restricted to 0 and 1, these are probabilities. Okay. So then what we can do is, if we know the total number of Oscars that they had, then we can use the curve to predict the probability of winning. Okay, where a 1 is winning. Okay. So here we use the curve to predict the probability of winning, which is the case 1. Okay, so that's the outcome of 1 is winning. And so so to get this S curve, we have to manipulate things a little bit. Okay, it's cool because it ends up being a linear function, but the thing that we're estimating is not linear. And so let's see here. To get from this curve, so how do we get the equation for this curve? Okay. So we will now we will now look at how we get the equation for this curve. This S curve. S club. Ain't no party like an S club party. Gonna show you how. Anyways, probably too old of a song. Anyways, S Club. So S Club 7. So what we need to talk about, and this is really important in kind of life too, is that when we say odds, a lot of people think that we're talking about probabilities. Now, odds are not probabilities. Okay, so they're related to probabilities. So for us in data science, statistics, whatever, you want to be really careful about your use of odds, right? The term odds means something special. Okay, and so here I'm going to highlight that because it is so important. So if we have an estimate of the probability, then the odds, so if p hat is the probability of an event, then the odds of that event are p hat over 1 minus p hat. Okay, so what we're saying here is if p hat is some probability of an event, then the odds of that event, of the event, is going to be p hat divided by 1 minus p hat. What's this saying? This is the probability of the event happening. We know that. We just established that. But 1 minus p hat is the probability of the event not happening, right? So it's a ratio of the probability of things happening over the probability that they won't happen. Okay, so that's really important, right? So odds are not probabilities, they're related, right? But they've got an example here. So if you have the estimated probability is 2 over 3, right? 0.66666, whatever, then the odds measure is going to be, so then the odds are going to be 2 over 3 over 1 over 3, the probability of it happening over the probability of it not happening, which is actually 2, which means that the odds are 2 to 1 that the event will occur. Okay, so the odds go from 0 to infinity. Okay, and so when we look at the probability only ranges between 0 and 1, but now the odds are going to go from 0 to positive infinity. Okay, so there's a change there. Okay, so what we do is we take the natural log of the odds. And so we call that the log odds or the logit. I don't know, but that's what it is. Yep. So the logit or the log odds. And when in statistics, especially, whenever we talk about the log, we never, ever mean log base 10. That's for, when you're dealing with sound or frequencies and stuff like that, they deal in base 10, but so basically only physics is in base 10. Everyone else is working usually in log base E, so the natural log. So for us, so I get sloppy, and when I read the natural log, I just read it as log, and that confuses people in the beginning, but it's good to kind of get used to. So especially if you're, in biology or basically anything, then we use the log, the natural log, as our log. Okay, so that's just a little tidbit. Okay, so what we do is we use the log odds. We replace our y with the log odds. That seems weird. right? But that's what we do. And then what we're able to do is we can estimate the log odds with a linear regression. That's nice because we know how linear regressions work, right? And so that's really nice. So here, we estimate the log odds with a linear model. Okay. So what we can do is we can find these coefficients with the exact same methods that we used in linear regression, even in time series. We can use those same methods, and now we're just back to a linear model, and that's really nice. But what we're trying to do is we're trying to estimate the log odds, and that's really hard to interpret, right? Because each of the coefficients that we find are going to be relating to the log odds. Now that's weird, right? And so, right, so where I'm at here is here. For example, if you find a slope of 0.596, what does that mean? It means that for every additional value in X, in this case, they're talking about for each additional Oscar nomination, right? What we're saying is that its log odds of winning the Best Picture awards increases by 0.596. That's hard to wrap our heads around because then we have to kind of unravel the log odds. That's not something that we're keen on doing, right? And so what we do is we just do it once, and then we can use that for interpretation. So what we can say is that the number of Oscar nominations is linearly related to the log odds, but we want to talk about ideally the probability, right? Not just the odds. Then we could raise it to the power of, or e to the power of whatever, and then we could look at the odds. But what we actually want is the probability, right? And so we have to unravel the odds to get to the probability. Now, let me see if I can. I'm going to copy this because I actually want to work through this a little bit. Crop. Okay. Because what we have, so for example, if we start with a shorthand of this model, let's have two predictors in there, so X1 and X2. So then what we can do, for example, if we have the log odds, so here, this is the log odds. Is predicted by some B0 plus B1 X1 plus B2 X2. Let's keep it a little bit simple. We've got two predictors in there, but that's pretty good. Of course, it extends to this full length, but I don't want to write all those out. I guess I could, but it's nice to see the shortened version. And so, for example, if we have this, and what we're trying to get is we're trying to get this p hat, right? We don't want to talk about how B1 affects the log odds. We want to talk about, okay, how are the probabilities affected, right? Because we're trying to model the probabilities. And so what we would do, right, to shake out, now it's just a math problem. We want to shake out this log. And so we can raise both sides to the power of e to the ln of p hat over 1 minus p hat. A little bit sloppy there. But then we have e to the b0 plus b1 x1 plus b2 x2. this goes away, right? And so what drops down is I have p hat over 1 minus p hat is e to the b0 plus b1 x1 plus b2 x2. Couple of ways you could go about it, but if you're trying to solve for p hat, I would probably multiply 1 minus p hat over to this side, and then move it over to the side here. So I get p hat is 1 minus p hat times e to the, and maybe what I'll do, well, first I'll paste this here so I don't lose it. And then what I'm going to do is I'm going to copy this. I don't have to write it out every time. How's that for cheating? Paste. Okay. So then if I expand this out, right, then I get p hat is 1 times this, minus p hat times this, e to the power of whatever, e to the linear model, let's call it. Okay. And then what can I do? What can I do? What can I do? Well, I can add p hat to both sides, trying to bring all my p hats to one side. So then I have, oops, p hat plus p hat times this equals this. Okay. And then I can pull out, what happened here? Okay. Pause. Okay. Figured it out where I tripped up. Here we go. So the reason I was getting kind of a little bit weirded out is because this is all fine and we want to bring the p hat over here, and then we want to isolate the p hat because that's what we're trying to solve for. And then I was looking at this and I'm like, yeah, it looks like we're on the right track, and we are. It's just that this equation here doesn't look like this equation here. Okay, so what happened here? Well, the problem is they're the same, they're equivalent, but we don't want to have to enter our model twice, right? And so to get away from doing that, we, and I don't know why I tripped up on this, but anyways, what we do is we factor out, no air quotes, we factor out a version, so e to the b0 plus b1 x1 plus b2 x2, we factor it out of 1. Now, remember, e to the power of 0 is 1. So as long as I make sure that I have a power of 0 total, then I can rewrite this 1 as e to the power of something. So what I'm going to do is I'm going to rewrite it as e to the b0 plus b1 x1 plus b2 x2 minus b0 plus b1 x1 plus b2 x2, right? E to the power of 0 here, e to the power of 0 is 1. So I'm replacing 1 with this larger kind of nasty formula, but it is all in the interest of saving us some work later on. Right, so then what I can do is I can, using the exponent laws, right, I can break this up into 2 exponents. So now I have another version of e to the b0 plus b1 x1 plus b2 x2 times e to the negative, and then it's all negative, b0 plus b1 x1 plus b2 x2, which I could expand that negative if I wanted to, but sometimes it's nice to just have it on the outside. So then once I have my 1 rewritten as this big nasty number, why do I think it would be a good idea to work through this with you guys? It's okay. It's good to see where it came from and that it's not that scary, and that you could arrive at it as long as you remember that you're estimating the log odds, and then everything else would fall into place. Extend this line here. Okay, maybe this one too. So now what I have is I have a common factor here that I can pull outside. And so now I can cancel here, right? I can cancel this E with this E because it's a common factor. And so I'm left with 1 over 1 plus E to the negative and then in brackets, right? You want to have your linear equation up here. Okay, so that's how we get those P hats, sorry, the probabilities, the predicted probabilities. And then this is, oops, kind of lagging there. So that's where that equation comes from. And of course, it extends to, we didn't really do anything. I just copied and pasted the model, the linear model. So it doesn't matter how big it is. I just wanted to have just 2 x's just for simplicity's sake. But of course, it extends to q x's if you want to. Okay. So now we have this logistic function, and the logistic function is what gives us our predicted values. Okay. So we use the logistic function to calculate predicted probabilities. Probabilities of being in class 1, but we'll leave that. Okay. Let's see how much I would have to bring up top here. So what we're talking about here, once we have this S curve, right, and that comes from this very non-linear predictor, right? So it's no longer linear, right? And so this P hat, this is what gives us the S curve. Okay, so the P hat is the S curve. And you can see how it takes x1 all the way up to xq, and all of a sudden it doesn't look very linear. It's e to the power of something, and 1 over that kind of messes things up, right? And so what we have is this non-linear relationship, right? Especially if you see this S curve. Okay? So how we interpret things and how things change are going to depend on kind of where we started. Okay? So the effect of increasing the total number of Oscar nominations, which in our case is the X, right, on the probability of winning the Best Picture award depends on the original number of Oscar nominations. So what is the benefit of 1 additional Oscar nomination if we started at 4, for example? So if the total number of Oscar nominations is 4, then what's the benefit? So what's the increase in probability of winning Best Picture if you increase from 4 to 5 nominations? So we can use the formula, right? And we've got the model here, so we can just apply that. And I can't remember if I brought it in somewhere. Oh yeah, here. So this is the model that we built on the log odds, right? And that's what we're using in our P hat. Okay, so here we can find the probability of winning if we have 4 nominations is 0.021, not very good. And if we have 5 so if we increase to 5 nominations, it increases to 0.038. So now we're on this S curve, and we're increasing our probabilities, and we see an increase of 0.017. That's not a number that's in our formula anywhere. So that's not what we're used to, but that's how this nonlinear relationship works. So whereas if we started with 8 nominations, looking at here, then the probability of winning is 0.191. That's pretty good. Right? So if we go from 8 nominations to 9 nominations, our probability jumps to 0.299, right, which is an increase of 0.108 or 10.8%, right? So it depends on where we started, right, because we have this S curve. And so if we start at a higher number, then the benefit increases. Okay. So once we have these probabilities, then we can use those probabilities just like we were in the previous section where we were saying, okay, if the cutoff value is 0.5, that's how I'm going to decide if they are predicted to win or not, right? And so we classify an observation by computing the probability of being in class 1. And let me see, I'm trying to highlight something, but I can't find it. Maybe I'll just highlight this, I guess. It is what I wanted to highlight. So, right, we can calculate each of the probabilities in all of these cases, right? 4 nominations, 5 nominations, 8 nominations, 9 nominations. Would we predict them to win? No, because each of these probabilities are less than 0.5, right? Even though there's an increase and whatever, all those probabilities are less than 0.5. But there is some point where we reach a number of nominations that are going to yield probabilities greater than 0.5. So if I just grab that S curve, copy. All right. We can look at these and we can say, okay, well, at some point here, at some point, I have a cutoff of a probability of 0.5, which means that at this point, roughly, now I'm not drawing very well here, right? But roughly at a little over 10 nominations, so you'd have to have more than 10 nominations in order to have a probability of higher than 5 of winning, right? So we can use this curve and we can find the cutoff. Now, remember, I'm not drawing very well. This is probably not straight. You'd have to use software, right? But roughly there. And then we would need some number of nominations. So all of these would be predicted to be in class 0. So they would not be winning. So here, all of these predicted 0. And these would all be predicted 1. That's not necessarily the case, right? But those are our predictions. Okay. So if we have a look at our data, right now we can start to go back to the previous section where we can look at, okay, if I predicted that they were in class 1, so they were going to win, what actually happened, right? How was I wrong? Was I right? Whatever. So we have some total number of Oscar nominations, and we can find the probability, the predicted probability of winning, 0.89, 0.58, 0.44, 0.07. And so here, if we use a cutoff of 0.5, right, then these 2 are winners and these 2 are losers. But what actually happened is we had 1 winner and 1 loser in the winner category and a loser and a winner in the loser category. So that's confusing. This is just an excerpt, right, to show you all the different options. But from here, we would compare the predicted classification to the actual classification using methods from section 9.2, right, from last day. So then here we consider the performance measures from section 9.2 to evaluate the model. Okay. So that's how we decide, right? You can make a confusion matrix to start, and then you know, how many are actually in group 1, how many were predicted to be in group 1, how many of those were predicted to be in group 0, etc. And then you can calculate your class 1 error rate, your class 0 error rate, your specificity, your sensitivity, your precision, your F1, all kinds of fun stuff, right? So you just need a method of predicting, and this is one. Okay. So while a logistic regression model used for prediction should ultimately be judged on classification performance, on the validation and the test set, so that's referring to what I said up here, right? So we look at the performance measures that we talked about a lot in section 9.2, but there are other things that we can look at. Okay, so Mallow CP is one of those, and I can't remember what the C stands for. P is probably number of predictors or something. But what it does is if you get a small value of Mallow CP, then you tend to have smaller mean squared error. Okay, and that's a good thing, right? But then models with a value of Mallow CP, now you'd have to get R to give you the Mallow CP, but if it's roughly equal to the number of coefficients in the model, then you're going to have less bias, right? And that's a good thing too. So, so a kind of a trade-off situation once more. Okay. I think that's it for logistic regression. Next day, we'll talk about K nearest neighbors, which is another classification method. And so I hope you have a good weekend, and I'll see you next week.